Light curves exactly 1.75 arcseconds when passing through the gravitational field of our Sun. Scientists at the 1919 Eddington expedition verified this staggering claim with 100% certainty. But your brain interprets gravity as a downward force instead of a geometric warp. Albert Einstein dedicated 8 years to a single vision involving a man falling from a rooftop. He replaced Newton's rigid clockwork universe with a living fabric warped by the weight of stars. This journey did not begin in a grand laboratory, but in the mundane quiet of a Swiss patent office in 1907. While sitting at his desk in Bern, Einstein experienced what he would later call der glücklichste Gedanke meines Lebens, the happiest thought of his life. He imagined a man falling from the roof of a house. In that terrifying instant of free fall, the man would not feel his own weight, his gravity, and to any other mind this was a macabre curiosity, but to Einstein it was the key to the cosmos. It was the equivalence principle. If gravity and acceleration were two sides of the same coin, then gravity was not a ghostly force pulling objects across a void. Instead, it was a byproduct of geometry itself. But translating this physical intuition into the language of the universe required a mathematical weaponry Einstein did not yet possess. In 1912, he returned to Zurich and turned to his old classmate, the mathematician Marcel Grossmann, pleading for help in navigating the treacherous waters of differential geometry. Grossmann introduced him to the work of Bernhard Riemann, showing him that the curvature of a four-dimensional manifold could be described using tensors. For years, Einstein struggled, discarding brilliant ideas and falling into mathematical traps that nearly led him astray. By 1915, he was living in Berlin at the Kaiser Wilhelm Institute für Physik, working under the immense shadow of the Great War while his health failed and his family life crumbled. The pressure reached a breaking point when he realized the formidable David Hilbert, perhaps the greatest mathematician of the age, was closing in on the same solution. In a breathless, desperate race across 4 grueling weekly lectures delivered to the Prussian Academy of Sciences throughout November 1915, Einstein refined his work in real time. On November 25, he finally presented the elegant final version of the Einstein field equations. He had found the master key G mu nu equals kappa T mu nu. Newton's gravity was dead. For over 2 centuries, the universe had been a rigid, clockwork stage. Isaac Newton's law of universal gravitation was the undisputed script of the cosmos, describing a world where gravity was a mysterious, invisible tether acting instantaneously across the void. If the sun were to vanish in an instant, Newton's equations implied that the Earth would fly off into the dark at that very same moment. But in the early 20th century, Albert Einstein realized a terrifying contradiction that threatened to bring the entire edifice of classical physics crashing down. His 1905 theory of special relativity, the Special Relativity theory, had established a cosmic speed limit nothing, not even the influence of gravity. This was the Newtonian conflict, an action at a distance that defied the laws of the universe. To solve this, Einstein had to do something unthinkable. He had to tear up the stage itself. By 1912, Einstein had returned to Zurich with a radical intuition, but lacked the mathematical tools to express it. He knew that gravity was not a force in the traditional sense. It was an effect of the geometry of the world. He reached out to his former classmate and close friend, the mathematician Marcel Grossmann, with a desperate plea for help. Grossmann introduced Einstein to a world of mathematical abstraction that physicists of the era rarely touch, the non-Euclidean geometry of Bernhard Riemann and the complex tensor calculus developed by Gregorio Ricci, Curbastro, and Tullio Levita. Together, they labored to find the mathematical language to describe a 4-dimensional manifold, the union of space and time into a single, flexible fabric known as spacetime. Imagine a vast, taut silken sheet stretched across the infinite blackness of the void. In Newton's world, this sheet was flat and unyielding, and planets were pulled across it by invisible strings. But in Einstein's vision, the sheet was soft. When you place a heavy mass like the Sun upon it, the fabric does not merely hold the weight, it curves. It warps and stretches, creating a deep well in the geometry of reality itself. A planet like Earth does not orbit because it is being pulled by a force. It orbits because it is caught in the curvature of that well, rolling like a marble around a bowling ball on a trampoline. This was the birth of the general theory of relativity, or allgemeine Relativitätstheorie theory. It was a paradigm shift that replaced force with form. The culmination of this struggle was the Einstein field equations G index mu nu plus lambda G index mu nu equals kappa T index mu nu. This elegant string of symbols described a breathtakingly simple yet profound reciprocity. Matter tells spacetime how to curve, and spacetime tells matter how to move. But this was more than a beautiful thought experiment. Einstein needed proof. He found it in a century-old mystery involved. For decades, astronomers had noticed that the perihelion of Mercury, the point in its orbit where it is closest to the Sun, shifted by a tiny, unexplained amount of 43 arcseconds per century. Newtonian mechanics could not account for this ghostly wobble. In November 1915, during a series of grueling lectures at the Prussian Academy of Sciences in Berlin, Einstein applied his new equations to Mercury's orbit. When the numbers emerged, they matched the 43 arcsecond discrepancy exactly. Einstein was so overcome with emotion that he suffered heart palpitations, later describing it as a moment where something within him snapped. He didn't just feel he had discovered a law of nature, he felt he had peered into the very mind of the universe. Yet, this was more than a correction of planetary paths. They predicted gravitational redshift, the idea that clocks would actually tick slower near a massive body where gravity is strongest. The first hint that time is not a universal constant, but a local experience. He saw that light itself, being massless, should still be. If a ray of starlight passed near the Sun, it wouldn't move in a straight line, it would bend. This realization turned the universe from a cold, empty container into a dynamic, breathing. Everything we perceived as the pull of the cosmos was merely the geometry of the invisible, a silent architecture of curves and valleys that dictated the fate of every atom in existence. The guns of the Great War had finally fallen silent, but the world they left behind was a jagged, broken mirror. While Europe struggled to piece itself back together amidst the influenza pandemic and the ruins of empires, a different kind of order was being sought in the heavens. This was a moment of profound tension between the old world of Isaac Newton and the radical new vision of Albert Einstein. Einstein was then isolated in Berlin, his body frail from the wartime blockade and a grueling work schedule, yet his mind was roaming the vast, non-Euclidean curved spaces of his imagination. He had predicted that the Sun's gravity would bend starlight, a claim that struck at the heart of classical physics and challenged the But to prove it, someone had to venture into the shadow of the moon during a total solar eclipse. This task fell to Frank Watson Dyson, the Astronomer Royal, and Arthur Stanley Eddington, the director of the Cambridge Observatory. Eddington was a man of deep, quiet convictions, a Quaker and a dedicated pacifist. He had spent the war years as a conscientious objector, nearly facing imprisonment for his refusal to fight. To him, science was the only language capable of transcending national borders. Verifying a German theory in the wake of such a brutal conflict was, for Eddington, a sacred duty, a way to use the stars to heal a planet that the logistical challenge of the 1919 expedition was nearly insurmountable. In a world still reeling from the chaos of the Great War, with shipping lanes dangerous and resources scarce, Dyson organized two. One team was dispatched to the town of Sobral in the dry hinterlands of northern Brazil, while Eddington himself led another to the remote, volcanic island of Príncipe in the Gulf of Guinea off the west coast of Africa. They were hunting for the Hyades, a bright cluster of stars that would be temporarily visible near the limb of the eclipsed sun. The goal was to capture their light on glass photographic plates and measure a deviation so slight it was equivalent to measuring the width of a human hair from several meters away. Einstein's general relativity predicted a deflection of exactly 1.75 arcseconds, while the old Newtonian model, treating gravity as a force rather than a geometric curve, predicted only half that amount, roughly 0.87 arcseconds. This wasn't merely a debate over decimals, it was a trial for the very nature of reality. It would determine whether space was a cold, empty stage or a living, warping fabric that everything they believed up to this point was wrong. On the day of the eclipse, the island of Príncipe was gripped by a sudden tropical rainstorm. Eddington, who had traveled thousands of miles across a fractured world, watched in near despair as thick clouds threatened to erase years of Einstein's mathematical labor. He was a man who believed in the elegant precision of the universe, yet here he was grappling with the chaotic humidity of West Africa. At the last possible second, as totality began and the sun's corona flared into the darkened sky, the clouds parted just enough. In those 5 minutes of unnatural, eerie twilight, the team worked with a frantic, rhythmic intensity, swapping heavy glass plates in the humid air while the local wildlife fell silent. They were essentially taking a census of the stars to see if the sun's mass had pushed them out of their rightful Newtonian places. It was a bridge of light reaching out from the distant Hyades, grazing the warped spacetime geometry near our sun, and finally landing on a fragile piece of glass in the hands of a peaceful astronomer. While the team in Sobral battled intense heat that caused their primary telescope to lose focus, Eddington began the painstaking work of development in a makeshift darkroom. These plates were more than just astronomical records. They were the first physical witnesses. Back in London, the results would eventually be presented to a joint meeting of the Royal Society and the Royal Astronomical Society, but in that moment on Príncipe, Eddington was the only person on Earth who knew for certain that the universe had just changed forever. He had found the 1.61 arcseconds of deflection that confirmed Einstein, moving physics away from the instantaneous action at a distance and into a world where mass tells spacetime how to curve and spacetime tells mass how to move. On the morning of May 29, 1919, a shadow began its slow, deliberate transit across the face of the sun, casting a cold, unnatural twilight across the Atlantic. In the remote jungle clearing of Sobral, Brazil, and on the humid, rain-soaked island of Príncipe off the coast of West Africa, 2 small bands of astronomers waited with the quiet desperation of men who knew they were about to witness the birth of a new reality. They were hunting for a shadow within a shadow, the faint, ghostly pinpricks of the Hyade star cluster that would only be visible during these precious minutes of totality. The stakes were nothing less than the geometry of existence itself. If Isaac Newton was right, the gravity of the sun would tug on the passing starlight, bending it by a mere 0.87 arcseconds. But if Albert Einstein's radical vision of a warped 4-dimensional manifold, that deflection would be exactly double 1.75 arcseconds. This wasn't just a measurement, it was a verdict on whether space was an empty, passive. On Príncipe, Arthur Stanley Eddington battled through heavy, rhythmic rain and thick cloud cover that threatened to ruin years of planning and months of travel. Only in the final seconds of the eclipse did the haze clear just enough, allowing him to capture the photographic plates that would change the course of human history. These plates were more than just images, they were the first maps ever drawn of a curved universe. When the expeditions finally returned to England and the painstaking analysis began, the atmosphere in the scientific community was electric with a tension that felt almost physical. Using the delicate micrometric measuring machines at the Cambridge Observatory, Eddington and Frank Watson Dyson compared the positions of the stars captured during the eclipse to their standard positions in the night sky. The results were staggering and undeniable. The Sobral expedition recorded a deflection of 1.61 arcseconds, while the Príncipe measurements, though taken through thinner clouds, hovered around 1.98 arcseconds. Both figures, despite their margins of error, were far closer to Einstein's revolutionary prediction than the Newtonian. On November 6, 1919, at a joint meeting of the Royal Society and the Royal Astronomical Society in London, the verdict was delivered to a packed, breathless hall. Beneath a portrait of Sir Isaac Newton, Dyson stood and announced that the observations from the eclipse expeditions unequivocally supported. In that room, the clockwork universe of the Enlightenment was dismantled. The Newtonian dream of an absolute, unchanging space had been replaced by a dynamic, vibrating fabric that the aftermath was a seismic shift in global consciousness. Almost overnight, Albert Einstein was catapulted from the quiet, dusty halls of the Kaiser Wilhelm Institute into the blinding, chaotic light of international celebrity. The Times of London ran a headline that famously screamed revolution in science, new theory of the universe. A world weary from the horrors of the Great War, a world that had spent 4 years watching humanity tear itself apart in the trenches, suddenly looked up at the stars and saw something beautiful. Einstein became a global icon, a secular saint of the intellect whose wild hair and deep, soulful eyes seemed to reflect the infinite mysteries he had unraveled. He had done the impossible. He had looked at the invisible curves of the void and found a way to read them. This moment changed the role of the physicist forever. No longer just a researcher in a lab, the physicist was now a philosopher, poet, a guide. The confirmation of the eclipse didn't just prove a theory, it provided a collective sigh of relief for a fractured world, proving that through the language of mathematics and the courage of observation, humanity could still reach out. The 1.75 arcseconds were small, a distance no wider than a silver coin seen from a mile away, but they were the thin crack in the door through which we first glimpsed the true, terrifying. Space was no longer a void, it was a topography, and we had finally learned how to navigate its curves. Einstein didn't just solve a puzzle, he released a ghost into the machinery of reality. In the frozen trenches of the Eastern Front in 1916, a German physicist and soldier named Karl Schwarzschild looked into the heart of the field. He sent a letter to Einstein from the Russian front, describing within that math, Schwarzschild discovered a mathematical singularity, a place where gravity becomes infinite and time itself grinds to a halt. Einstein was initially skeptical, believing that nature would surely protect us from such monstrosities. He could not yet conceive that the universe would allow for the existence of what we now call black holes. These are the ultimate expressions of general relativity, regions of space where the geometry of reality is tied into a knot of infinite curvature, creating an abyss from which even light cannot escape. They are no longer mere mathematical curiosities, they are the anchors of galaxies, the most extreme laboratories where the laws of physics. But Einstein's vision, in 1917 he applied his equations to the entire universe itself. He found his math was too dynamic, it insisted the cosmos must either be expanding or contracting. Disturbed by this, he added a term known as the cosmological constant, or lambda, to force the universe to remain static and eternal. It was a rare moment of hesitation from a man who usually trusted his physical intuition over existing dogmas. A decade later, when Edwin Hubble observed distant galaxies fleeing from us at incredible speeds, Einstein famously abandoned the constant, calling it his greatest blunder. Yet, in a twist that would have delighted him, modern cosmologists have brought lambda back to explain dark energy, the mysterious force accelerating the expansion of the universe toward an unknown fate. But the legacy of general relativity is not just found in the depths of space, but in the palm of your hand. Every time you use the GPS on your smartphone to find a local coffee shop or navigate a new city, you are witnessing Einstein's genius in action. Because the Earth's mass curves the spacetime around it, the passage of time is literally different at higher altitudes. Clocks on GPS satellites high above the planet run slightly faster than clocks on the surface. If engineers didn't use the general theory of relativity to correct for this gravitational time dilation, your position on the map would drift by 10 kilometers every single day. The world's navigation systems would collapse into chaos, proving that the most abstract mathematical discoveries can have the most concrete consequences for human life. Exactly 100 years after Einstein presented his final equations to the Prussian Academy of Sciences, the universe finally spoke back. On September 14, 2015, the Laser Interferometer Gravitational Wave Observatory, or LIGO, felt a tremor. It was the first direct detection of gravitational waves, ripples in the fabric of spacetime itself. These waves were caused by the collision of two massive black holes over 1 billion light-years away. The signal was so faint that it moved the observatory's mirrors by a distance smaller than the nucleus of an atom, yet it confirmed Einstein's final great prediction. For the first time in human history, we didn't just see the light from the stars, we felt the vibration of the vacuum. We are no longer just observers of the cosmic stage, we are listeners to the song of the spacetime manifold itself. Einstein's discovery changed physics because it changed our relationship with the infinite. It showed us that we live in a universe that is flexible, dynamic, and inextricably linked to our own perspective. We are travelers on a curved landscape bound by laws that connect the fall of a stone to the birth of a world. As we look toward the future, toward the secrets of dark matter and the potential of a multiverse, we are left with the realization that the more we map the stars, the more we are exploring the profound architecture of reality itself. The universe is not only stranger than we suppose, it is stranger than we can suppose. If this journey through the mind of a genius left you thinking, subscribe and hit the bell. Tell us in the comments